Okay, everyone, let's make a start. Thank you all for coming. I'm sure you're here to see the interesting presentation we've got for you from Ahmed Jamori on motion control of complex robotic systems. He gave a very good talk yesterday on marine robotics as well, so keep an eye out for the link for that. I don't think there's anything else to say, so I'll hand over to you yeah, enjoy the talk.
Thank you very much, Mark, for this introduction, and thanks once again for the invitation. So it's my pleasure to join you today to give you this presentation that summarizes roughly my research activity these last years. So I will talk about motion control of complex robotic systems. First of all, let me introduce the lab. So actually, our lab is situated in Montpellier. As you can see here, it's the map of France. So Montpellier is a city in the south of France. Very nice city, as you can see from the pictures. We have beaches, we have very nice weather. According to the statistics, we have more than 300 sunny days every year. And then Montpellier is known by many things, just a few of them. First of all, the oldest faculty of medicine in Europe and maybe in the world is situated in Montpellier, founded around 1220. It's a very nice city. Seventh biggest city, we have 300,000 people in the city, but a big amount of these population are students. We have 70,000 students in 2 universities in Montpellier. Our research lab is called LIRM, and LIRM is coming from Laboratory of Informatics, Robotics, and Microelectronics of Montpellier. So as in a research lab in the world, so we belong to the University of Montpellier, but also we belong to another institution. It's the biggest research institution in Europe. It's called CNRS. It's the National Scientific Research Council. And it means that we have researchers from this institution and we have faculty members from the University of Montpellier. Our research lab is organized in 3 departments: computer science, robotics, and microelectronics. And we are more than 440 people, including permanent staff, like faculty members and full-time researchers like me, 170 PhD students, and administration staff also organized in these 3 departments. So, first of all, to start the topic of today. So nowadays we can have a lot of kind of robots, and what we can notice is that we have more and more complex robotic systems. Here are just some examples of them. And the question that we may ask, how we can deal with the control of those systems. So this is the topic of the presentation of today. So the rest of the presentation we organize as follows. So I will first focus on the control problem of complex robotic systems. I will introduce what I mean by a complex robotic system. Then I will try to focus on several applications on which I have been working last years. So the control of rigid parallel kinematic manipulators, high-speed parallel robots, the control of cable-driven parallel robots, the control of tethered autonomous underwater vehicles, control of bio-inspired underwater vehicles, and the control of wearable exoskeletons for rehabilitation. And I will conclude my presentation by the end. So let's get started regarding complex robotic system. As you have seen from the first video, nowadays we have a very complex robotic system, and the question that we may ask, from where this complexity may come. So actually we have several sources of this complexity. So it may come from the structure itself. It may come from the dynamics. We have very highly nonlinear dynamics. It may come from the actuation of the system. We may have under-actuated systems, over-actuated systems, actuation with saturation, unilateral constraints, and we may have also complexity coming from the interaction between the robot itself and the environment. And also we have to consider the real-time constraints like the sample time, like the computing time, to be able to implement and test the developed controllers. So my research activities have been focused on the development of nonlinear control schemes coming from like nonlinear adaptive, nonlinear robust, and nonlinear predictive control. And the idea was to develop new controllers and to do the real-time experiments as validation of those developments. And also we have to focus on the stability analysis, the theoretical stability analysis, to prove that those controllers are stable based on Lyapunov concept. So just to summarize, my activities can be considered as a bridge between 2 things, between the automatic control aspects, like here, control design, stability analysis, feed time convergence, and so on, connected to the robotic aspects like real-time experiments, under actuation, over actuation, real-time constraints, and so on. So just to sum up, in this slide, so I'm interested in linear control of complex robotic systems with these main 5 applications. Let me just say a few words, but in the rest of the presentation, I give more details. So the first application, it concerns the control of parakinematic manipulators, as you can see from this picture. Then I have been interested also in the control of cable-driven pararobots, the control of autonomous underwater vehicles, the control of bio-inspired underwater vehicles, and the control of exoskeleton. So the rest of the presentation will be around these 5 applications, and let's start with the first application. So within this first application, I have been advising 6 PhD students working on this topic to develop several control schemes. They are coming from different countries. As you can see, we have an international team of researchers, and all the developments have been applied on those experimental platforms that you can see here to validate those controllers. So to get started, let me show you 4 applications where we are using these kind of robots, parakinematic manipulators. So the first application here is a high-speed pick-and-place applications, where the idea is to get an object from the data and put it in a box, and it's very simple operation. However, what we are looking for here is the high speed and acceleration. We want to increase the number of picks per minute. So this is the first application. The second one, it considers machining using parakinematic machines, as you can see here. So where we need to manage this interaction between the tool and the piece. The third application is waste sorting, and the idea is to use also a high-speed pararobots to do the sorting of the waste, as you can see here. And the last application, as you can see, it's the driving simulator, where we use a pararobot to generate these dynamics of the car or the airplane or anything like that. So I have been interested in those 4 applications, and let me say a few words about this. So pararobots, they have been developed for long years and with a lot of applications. Let me just cite some of those applications. So the first one is motion simulators. As you can see from the picture, flight simulators or driving simulators, boat simulator, and so on. We have also another application which is very interesting. It's the high-speed food packaging. We have applications in telescopes, we have applications in synchrotrons, machining, medicine, agriculture, waste sorting, space, and so on and so on. So this is some of the applications where pararobots have been used. And now in terms of research regarding this kind of robots, so we have several aspects. We have the aspects of modeling, the aspects of motion planning, the aspects of mechanism design, so stiffness design, for instance, architecture, optimization of the design, and we have the control aspect. So I have been interested in this last aspect concerning control. If we need to resolve the control problem, so we have to deal with highly nonlinear dynamics of those robots. We have to consider the uncertainties and external disturbances that may affect the robot itself, because there is an interaction between the robot and the environment. And also we have to deal with the problem of under-actuation. And this is under-actuation or over-actuation. Here, actuation redundancies means that you have more control inputs than degrees of freedom, and this may generate internal efforts that we have to manage when we design the controller. So in our case, we have been interested in improving the dynamic performance of those robots first. So we want to increase the motion speed and acceleration. We have been interested in the accuracy, to design a robot with an accuracy less than 10 micrometer of a position in the space. Then we try to look to the speed and accuracy at the same time, and we have been interested to test the robustness of all the proposed controllers, from adaptive, robust, and to compensate for the errors with the stability analysis and doing real-time experiments. Here is just a summary of the main contributions. I will not detail them, but just to see that we have a wide range of controllers. Most of them, they are either robust or nonlinear, or both, or adaptive, because of all the constraints, because of all the uncertainties and the interaction with the environment. So let me show you some of the obtained results. Here is a short video that shows you different place. This is a high two axes. Gravity. So here we have a maximum acceleration about 500 meter per second square as a maximum acceleration. This is the first experiment. Then here we designed a geofeedback adaptive controller where we reach an acceleration of 100 G. This means 1,000 meter per second. here I focus more on the obtained results. Then we, concerning the waste sorting, we developed a pick and throw method. Here we compare it with the classical pick and place. Pick and throw means that to throw the object, we are not obliged to go into the box to put the object, but we can throw the object. This is why we can have more picks per minute. You can increase the performance regarding speed. Here it's the same scenario with a high speed motion, and we compare the different ways that we can do, and you can see here the number of picks per minute. So we increase this number significantly compared to the different ways classical task. And here we compare the existing task with the proposed one, also for low speed and high speed, and show the obtained performance in this case. Now, the next application is for machining. Here we developed an adaptive gain rise controller to do the machining. So the idea is to design some reference trajectory to the machining, and then to follow those reference trajectories in precision to do the machining. So we go through some parts of trajectories like pick and place. We will be in contact with the piece sometimes, and sometimes away from the piece. And we have to follow those reference trajectories with precision. Then we into contact with the tool and the piece, and we have to follow with precision this reference trajectory. And the next application is for parallel robots, like used for flight simulators. And here the idea is also to develop robust controllers for the tracking of these kind of reference trajectories. And the idea is to improve the tracking performance in terms of precision. Here, as you can see, the plot of the reference trajectories is 60. Those robots, they have a small workspace. However, they have high dynamics, and also they have 6 degrees of freedom of the motion here of the moving platform. Here, as you can see, is the plotting of the reference of the tracking chaos, as you can see in the space. And in the end, the input force, the control input generated by the controller. And as you can see, the tracking performance was about 22 micrometer of precision of this reference trajectories tracking. So it's very, very high precise tracking. So this is the first topic. So one of the drawbacks of this previous kind of robots is the small workspace. You have seen it's a small workspace. So to resolve this problem, we can develop another kind of robots, which is called keyboard-driven parallel robots. What is the idea? Let me give you more detail. 2 PhD students worked on this topic, and 3 experimental platforms have been used to validate all the developments. So first of all, to introduce the context, if you see in the stadium for sports broadcasting, we use this kind of camera. And the camera is attached to cables. The cables, they go through the winches here, and you control the winch here to control the tension in the cable such that you will move the camera in this very huge workspace. So to increase the size of the workspace, you replace the rigid links by the cables, and then you control the tension of the cables to move here in this the huge workspace. However, we have a lot of control problems here. One of the big control problems is the control action, because actually if you have rigid links, you can push and pull in both directions. However, for the cables here, you need to keep the tension all the time positive. It means that you have unilateral constraints on the control inputs, and you need to design controllers able to manage this saturation or these unilateral constraints on the control inputs. This is one of the problems. We have also the problems of vibrations. If you have very long cables, when you move them, you may have this vibration. We have the problem of precision, and so on and so on. So to sum up, what is a cable-driven parallel robot? Here, as you can see, classical manipulators, you have the case of the previous robots, rigid links parallel robots, and you have the case of cable-driven parallel robots. We replace the rigid links by cables, and we have the moving platform in the middle, and we control the winches here to control the motion of the platform. So if we sum up, cable-driven parallel robots is the intersection between parallel robots and cable mechanism. And here you have some examples where we can use them. So we can use them for lifting applications, for motion simulation, for pick and place applications, 3D printing, bionic and rehabilitation, and so on. And we can find a lot of research topic in this field. So the configuration, for instance, the kinematics and statics, the dynamics. If you want to compute the dynamic model, for instance, the cables, it's not very easy to take the dynamics of the cable itself. So we will have a very huge dynamic model, and maybe in control implementation, it will not be possible to implement if you take all the details of this model. But you have to choose a compromise between the complexity and feasibility. And the last research topic, it concerns the control of these robots. So in our case, we developed a control solution based on model predictive control. So the idea, it was about installation of curtain wall modules on building facades like that within a European project. This is the proposed control solution based on a cascade control scheme with a cable tension control here as inner loop, and the outer loop is based on nonlinear predictive control solution. Some of the obtained results here we validate in the lab, the obtained results, and we tested first for a pick and place trajectory. So the idea is to move the moving platform, as you can see here, and to do the tracking of the different trajectories for a pick and place application. Here we set the maximum tension in the cable at 400 Newton. As you can see, our control inputs satisfy this saturation or this maximum limit in the tension of the cable. Then we reduce the value to 250. Now we don't need to go beyond 250 Newton in the tension of the cables. And as you can see, the nonlinear predictive control proposed respect this new saturation. However, we have to degrade the tracking of the different trajectory while respecting this high constraint in the control input in the tension of the cables. And you can see the obtained results here. Then we compare this proposed control solution with the classical PID controller and to see the performance. When we choose the nonlinear predictive control, we can deduce what is the reason here because of the constraint in the control inputs, saturation in the cables. This is why we develop this. Why we propose this control solution, because nonlinear predictive control can take into account implicitly the constraints in the control input. Now, the control of autonomous underwater vehicles for PhD students and several experimental platforms where we tested the proposed results. The question that we may ask to start the contest: why autonomous underwater vehicles? Let me show you this short video. So this was 2 years ago, and 5 people killed in this manned underwater vehicle. So this can justify the development of unmanned underwater vehicles, and this is topic of this part of the presentation. So when we develop underwater vehicles, they may be used for several applications. Here, some examples of them. So the inspection of underwater facilities, for instance, the problems of maintenance, the dam inspection, or offshore wind farms, for instance, inspection, or also underwater manipulation. So the main research topics in marine robotics, we can distinguish like the modeling problems, kinematics and dynamics. We have the problem of simultaneous localization mapping, the problem of motion planning, especially for some applications with many robots underwater. The actuator design itself, we can design several kinds of actuators like classical propellers or bio-inspired actuators, the problem of underwater communication, and also the problem of control. And I am interested in this topic of control, and the idea is to develop controllers for this case. Let me introduce the control problem formulation through these two main applications, where actually here we use the joystick to control the underwater vehicle. We have the feedback from the camera on board the vehicle. The first one from Symbolics, and the second one we visited some years ago, EDF, it's the electricity company in France, and the idea was to see how they do the inspection of dams like that. Every 10 years they have to do this inspection using an underwater vehicle, the operator here, and using the joystick to control the motion of the vehicle, and he has a feedback on the screen. So what you can notice from these two applications is the following. So as you have seen, we have a lot of oscillations. So the motion is not very stable. And so there is a lack of precision and it's operated in open loop. And also it's very difficult to be manipulated. So the idea we propose to do the automation of this task, at least partially or even fully, and to replace the joystick and operate by a control system. However, in this case, we have to deal with a lot of problems, like as have seen at the beginning, nonlinear dynamics, time-varying parameters, strong uncertainties, and so on. So we propose several controllers, as you can see here. most of them from adaptive control, robust adaptive control, saturation-based control, and so on. And we did several experimental results, and we show you some of them. Here, we design an observer combined with a nonlinear robust controller, and we do the tracking of the reference structure, as you can see here. We compare the classical RISE controller, which is a nonlinear robust one, with the extended one, the S-Plus RISE controller, which is a saturated one. And then we combine this thermos observer with this RISE controller, and we compare all of them here in terms of tracking of the reference trajectories. We are controlling 2 degrees of freedom, so the depth and the U. Here, the depth, and here is the U. And in this scenario, we test the robustness of the controller because, as you can see, we fix this sheet on the robot to change to introduce an uncertainty on the damping, and we fix here 2 clothers to change the buoyancy. And we keep the original nominal controller, and we compare the nominal case with this change case to test the robustness of the proposed controller in terms of tracking performance. So you can find more details in the paper, as you can see here. Let me go ahead. So the next one, some applications where we designed here a robust adaptive controller for underwater applications. And we did here the semi-autonomous underwater inspection of the ship hull. So like the depth and orientation of the vehicle are controlled automatically. And then here we have the feedback from the camera on board the vehicle. And the human can use the joystick just to move along X and Y to do the underwater inspection. Here, semi-autonomous ship hull inspection, we try to do the inspection of the propeller of the boat. So we try to go closer to the boat like that and to get some videos to do the inspection of the propeller of the boat, as you can see for this application. Here, as you can see, very stable images, and you can see very close. And then we have wall tracking. Here we used a stereo vision, 2 cameras, and we estimate the distance between the robot and the wall. This can be for a dams application, for instance, dams inspection application. So the depth, the U, and also the distance are automatically controlled. And the human has just to push the joystick to move along Y direction and to do the inspection in a very easy way. Now, the control of bio-inspired underwater vehicles. Let me introduce the general context. So all the previous robots that I have seen here for underwater, they are equipped with propellers. And now if you have a look to the sea animals, as you can see, you have some of them here, we can see that there is no propeller. So they use mainly fins to move underwater. Like the snaking, they don't have fins, but by undulation of the body, they can go through very confined environments. They can move in a very performant way underwater. And the question is, why we don't do bio-inspired underwater vehicles? This can be a very nice solution to inspire from those sea animals. So if we do a classification of the existing bio-inspired underwater vehicles, first of all, we can find undulatory fins, so robots equipped with fins, and the fins that are undulating. And by undulating the fins, you can move underwater the body of the underwater vehicle. And then you control the motion of those fins to increase or decrease the speed of motion and also the position. Then we can find oscillatory fins underwater vehicles, as you can see some of examples here. And the idea here also, it's the same. However, it's not undulating and it's oscillating the fins to move underwater. We have the class of legged underwater robots. They have legs here, as you can see, and they can move on the seafloor. We have E-like underwater vehicles. Here we control, they construct a module, and the job is the same module. They connect all the modules and they can move underwater. And the last one is a human-like robot from Stanford University, also that can be considered as human-like bio-inspired underwater vehicle. So main applications where those robots are used, we can find underwater archaeology, we can find diver following or diver cooperation as a good application, fish monitoring in aquaculture, and also military surveillance applications. In our case, we worked on this robot called UCAP. It was developed within this European research project at the University TalTech in Estonia. And the primary idea, it was for archaeology applications. So the idea is to design a small robot that can go inside a shipwreck and do this underwater inspection of the shipwreck. So first of all, we consider to not use the classical propellers, and we replace these propellers by fins. And the obtained design was this of UCAP using 4 fins, the green parts, as you can see here. So the robot is very small and it's for archaeology inspection. We use the video to identify objects of interest. It should be small and highly maneuverable, and it should be safe also for the human and the environment. We didn't use propellers because we can restrict the underwater visibility, because we may disturb the sediments, and also tether, because we go inside the shipwreck, so no need to use the tether because we have huge problems if you use the tether, and it has 4 actuators, 4 motor actuators, and 4 fins. So we have several control issues. First control issue is the which control mode, because actually depending on the orientation of the fins, you have 2 control modes. You have the hover mode and the cruise mode. So the hover mode is for high precision positioning of the robot. You can stay at a specific position very easily because the 2 fins are oriented like that. They compensate each other and you can obtain a very stable motion or positioning. However, for the second one, it's used to move from one place to another, so we have more force or more thrust pushing the robot in this direction. The second control issue, how it works now, the control itself. So the actuation, as I told you, it's thanks to these 4 fins. I want to move along the x-axis. It's very easy. I orient the fins like that, and then I move the fins. I will move in this direction. In the other direction, I will do something like that. So it's very easy to control each degree of freedom alone, X and Z and Y and roll each U. However, the question that we may ask, if I want to control 2 or 3 or 4 degrees of freedom at the same time. So the question, how I can orient the fins and how we control the fins to follow these trajectories on many degrees of freedom. And this is a control issue because we have the problem of under actuation. Then we have another problem because actually a dynamic model of an underwater vehicle is easy to find in a textbook. However, the problem may come from the dynamic model of the fin itself. You know the fin is flexible, and if you want to model the fin itself, you will have a strong, complex dynamic model of the fin. So we have to find the compromise between complexity and also real-time implementation of visibility of the dynamic model. In our case, we try to find a solution. As I told you, the control inputs go through the oscillation of the fin, so we can use 2 parameters. One of them, it can be the frequency of oscillation, it can be also the amplitude of the oscillation as a control input. So we did some experiments to identify the dynamic model of the fin with different frequencies here, and we increase the amplitude, and as you can see, the thrust is moving or it evolves depending on the amplitude of this oscillation. So we find the solution, we did some simplifications, and we come up with this model of the fins that represents the amplitude depending on the desired thrust that we want. Now, several contributions here that I will not detail, you can find them in the papers. We developed several controllers. I will show you some of the obtained results. One of the obtained results, it was to design a controller based on 2 feedback. So the first feedback is the camera coming, is the vision signal coming from the camera, and we want to combine it with the pinger, the acoustic signal, because we tried them, the pinger alone, acoustic signals, the camera alone, but both they have disadvantages. So we decided to do the data fusion between them to improve the performance using both feedback. This is the proposed control solution with the acoustic detection, visual detection, and the data fusion. And we used deep learning to detect the diver in the field of view of the camera. Now we obtain the results, and we show you a short video that shows you different steps that I explained. So we start first with acoustic tracking using just the finger. So the robot is equipped with 3 hydrophones. We have the finger held by the diver, and we do first the visual tracking, just the camera. The diver is moving, and you can try to follow the diver. However, the problem, if the diver is outside of the field of view of the camera, so we cannot do anything. And this is the limitation of this first solution. And also, if the diver is far away and the visibility is not so good, we cannot see the diver. So we cannot rely 100% on this signal on the camera. So this is why we tried another solution, acoustic tracking. And in this case, we have the advantage, whatever the position of the diver is in the front or behind and so on, so we can detect this signal. But the problem of using the acoustic signal is the precision. We can track this target, for instance, but when we reach the target, we continue turning around, and this is not a good solution because of the precision. Then we try to combine both. So the tracking here of a static target, which is fixed here, we go from this point to this point, and then for the last part, it was the tracking of the diver in real time. And based on these 2 modalities, it means that if we can see the diver, we rely on the diver and the finger, the acoustic signal. If you cannot see the diver, we will switch to the control based on this acoustic signal alone. And we switch between the two modalities depending on the situation. And the data fusion here for the diver tracking. And as you can see, the diver is moving and you is following the diver all the time. And we will not lose the diver in this case. And the last topic is control of exoskeletons. So to introduce this topic, we have the problem of spinal cord injuries. Here, as you can see, where it happened, the cord injury, and the consequence here, as tetraplegic or paraplegic and so on. And it's the problem. For the disabled people. Nice. So to introduce the general context of exoskeletons, let me introduce 4 issues of the society of today. First of all, we have the problem of aging of the population. Then we have another problem. It concerns the automation. Despite the automation of many tasks, thanks to robotics, we still have a lot of very difficult tasks done by humans. Also, we have the problem of wars in some places in the world. Despite the development of very nice cars of today, we still have traffic accidents. And what would be the consequence of all these 4 aspects? So, aging population, tired people with a lot of problems, amputee people, and disabled people, and so on. And the question that we ask, how we can help them. So, let me talk about the first problem. So, the aging of the population all over the world. Here is the population around 2000. And look to the colors here. It depends on the percentage of the population. And the color is becoming darker if the population percentage is higher. And here it's around 2000, 2015, and look to the projection 2050. So in many places in the world, we can have like more than 30% of the population, they have 60 years old or more. And those people, they will have a lot of problems. And one of the problems is can be the obesity, diabetes, anemia, cancer, and so on and so on. And the question that we may ask in this case, how we can, what would be the best solution for their mobility problems? So exoskeletons can be used as a solution. And one of the very simple tasks for us to do is to go from sit to stand. For any people in good health, he can do it very easily. However, for elderly people, it can be a challenge just to do this motion from sit to stand. And exoskeletons can be used as a solution. And in general, exoskeletons are used for many applications. So we have medical applications for rehabilitation, for instance. We have industrial applications like manipulating heavy tools. So exoskeletons can help the user to hold the weight of these heavy tools. Other examples like practicing sports, exoskeletons or daily life tasks, and military applications. When we talk about control, a typical control architecture for those systems, it can be represented by this block diagram. So we have the environment, we have the user or the wearer, we have the exoskeleton itself, and we have here the controller. And the control is based on 3 levels here: the high level, the mid level, and low level. And something which is very important, as you can see, which repeat everywhere here: safety, safety, safety. We need to take into account the safety of the user because we have a human inside an exoskeleton. So in our case, we have been interested in developing controllers for this exoskeleton. It was developed in this university in Paris, and in cooperation, we tried to find control solutions for this exoskeleton. And here, it's one of the typical application sit to stand tasks using this exoskeleton. And another application is the rehabilitation. So it's flexion extension of the knee, as you can see, where the user is in a sitting position and we control the exoskeleton to do this flexion extension task. Several control approaches have been developed here. I will show you just one of them. So we developed this model predictive control framework. Detailed here, we have the environment, we have the exoskeleton, the human. So the green parts are the different parts of this framework. So we have parameters identification first of the exoskeleton and the human. We have a nonlinear state feedback as an inner control loop, and the outer loop is based on model predictive control. We added a nonlinear disturbance observer to estimate the torque of the human. This is one of the big problems when the human is within the exoskeleton and you want to do assistance as needed, how you can evaluate the torque developed by the human. We do not have a measurement of this directly. And this is why we developed a nonlinear disturbance observer. And also we proved the equivalent stability of the proposed control solution. Some of the obtained experimental results here for this assisted as needed controller, we compared like PID controller, MPC, and explicit MPC, where we took into account the constraints in the control input, and we compared here the tracking performance of Gauss-free controllers. And here we tested the proposed control solution for walking control here. So we asked the users to work at abnormal, so something like that. So the left leg is okay, and the right leg is something like that, and we try to do the rehabilitation. So we say it was very difficult to do experiment on patients. This is why we took students, we asked them to do training for many hours to work something like that, abnormal walking, and then they wear the exoskeleton and we try to do the rehabilitation using this exoskeleton. Other control topics on which I have been working, but I will not detail them here, just to mention them. Two PhD students worked on this topic. It's the control of under-actuated mechanical systems with different applications, and the control of humanoid robots with one PhD student. Let me now conclude the talk of today. So I have been interested in control of complex robotic systems with several applications. I talked about the control of rigid parallel robots like this, the control of cable-driven parallel robots. I have been presented also the control of autonomous underwater vehicles, bio-inspired underwater vehicles, and the control of exoskeletons. I didn't talk about under-actuated mechanical systems and the control of humanoid robots. And recently, I started working on control of lead robots in extreme conditions, as illustrated by this slide. And for the perspectives, I continue working on the previous topics, and I will focus on some of them. Like here, we are interested in control of parallel robots, but here we are treating two problems. So the first problem is the geofeedback. So we have two sensors to measure the joints here, two measurements. However, we have a problem. We have a delay between the two measurements. So if you put that PID controller and you close the loop, it will be unstable. It's very unstable due to this delay. And we try to resolve this problem. And also we have also some flexibilities in the dynamics of this parallel robot. So we try to, and combining this flexibility with delay, it generates an oscillating motion. And the idea is to find the control solution to resolve this problem of oscillation, to have a precise motion without oscillations. The second topic, we have been interested in control underwater vehicles, but in extreme conditions. So in conditions where we have waves disturbing the robot, and we try to resolve the control problem in this case. And the third topic is concerns of these students, it concerns the control of systems like that. So we have here a boat or a ship tracked by renewable energy. We have a kite, and we use the kite and we use the wind energy to track this boat. So we have two control problems to resolve. We have the problem of motion planning, the motion planning of the kite trajectories depending on the weather condition, and also we have the control problem. And the last one here, I have been interested now to control vehicles that can fly and dive at the same time. It's a hybrid aerial underwater vehicle, and I have a PhD student working on this topic. So to finish my presentation, I have to thank all my PhD students. So 26 PhD students, 21 they defended, and 5 they are in progress. And I have to thank them a lot because all the results I am presented here, it's the effort of those students. Some useful links to end the presentation. All my research papers, you can download them on reprints on ResearchGate. So if you want more details about developed controllers. If you want to see more videos about my research activities, I have also a YouTube channel where you can find more videos to see what we developed as control solutions and the performance of those controllers. And by this last slide, let me thank you very much for your attention.
That's amazing. What a amazing array of research. Does anybody have any questions, either here or online?
Yeah, please go ahead.
Hi. Yeah, it's just so nice to see so diverse kind of range of application implementations. I have like two short questions. The first one is very far a bit. I don't see, like, I understand more or less like just by feeling what you mean by complex robotic system. But maybe could you be more precise on what you consider a simple robotic system and a complex robotic system, and how we move maybe in this kind of dimension?
Yeah. Yeah. So here I introduced the problem of complexity, as I told you. So for sure, depending on the system itself, sometimes you have several complexities or several things combined. Like, for instance, you can have a system with a complex structure, like many degrees of freedom. You have inside like the friction inside to take into account. You have the constraints. You have the nonlinear dynamics of the robot itself. You have the actuation, maybe under actuation or over actuation, the interaction of the environment, and the real-time constraints. So this is a very complex system. Now, what is simple? Maybe you can find some simple system. If you have a system where you have not to consider the friction, the dynamic model is simple to compute, and there is no interaction with the environment, and the real-time constraints are easy to satisfy. Maybe in this case, it's not be considered as a complex robotic system. So, but for sure, it's not so easy to find like a cursor that shows you this is simple and this is complex, because here we are considering a lot of aspects that makes the control design difficult. I mean, it means what? It means you take a classical control to take a PID and put it on this system, it will not work perfectly. Base tension, sometimes you can have a PID well-tuned that works very well. Base tension, this is in the nominal case. But take the same controller that works very well in this complex system and change the working conditions or the interaction of the environments, add uncertainties, dynamic disturbances, and so on. You will see that the PID cannot guarantee the performance. And in this case, you are obliged, you need to design a robust controller that will be able to compensate for this change in dynamics, in the environments, and so on. So this is what I mean by complexity in those systems.
And just a follow-up.
Yeah.
So my background is in swarm robotics.
Yeah.
When I think about complexity, I think about autonomous decentralization, self-organization. But you have a really diverse pool of robotic systems. I was just wondering, like, have you ever considered applying or implementing or trying with multi-robot systems, or maybe even with robot swarm that have more restrictions?
Yeah.
Is something that, or it was just never pick it up?
Yeah, I understand. Very nice topic. Yes, very nice topic. I never worked on swarm robotics because actually, because it's very interesting. But the problem is, if you take an example of those robots, like if you take these kind of robots, we need to design at least 2 or 3 robots to do the first tests. Okay, and for instance, for underwater communication, it's a big problem, and the coordination of the motion. But we need at least 3 robots to do this kind of application to design controllers. But up to now, I didn't work on this, but it's very, very nice topic. I fully agree. Yeah.
Anybody else have any questions?
Yeah, please.
Can you talk a little bit more about those underwater drones that you mentioned next year?
Which one?
The last thing that
the last, yeah.
future stuff that you're working.
Yeah. Okay. Okay. Yes.
Yeah.
Okay. Here, the idea is to have a drone. Okay. So a quadrotor that can fly, and we don't change anything with the same actuators, it can die. Okay. So we have to manage a lot of things. When we control the vehicle in the air, it's like any drone. There is no problem. We have to manage this transition. So the robot itself has to get from air inside water. And this transition is not so easy to manage. Then, when the robot is inside the water, you have to change the control. Because actually, you cannot use the same controller in the air and inside water. And the other problem is the propellers themselves. Because we have some few works in the world regarding this topic. You can find some videos of those vehicles. It works, but they design, for instance, in terms of control, most of the solutions they consider two controllers: one controller for the air, one controller for the underwater. And when they touch the water, they switch from a controller to other. In our case, we don't want to do this. We want to design one controller for both. So it should be robust enough. When we change here the medium from the air inside water, we keep using the same controller. So this is the novelty that we want to develop. Something else also, some of the solutions, they use just a set of propellers, okay? But the same propellers in the air and inside water, not the same speed of rotation, okay? In our case, we will use like two sets of propellers, aerial propellers, and in the down part, underwater propellers. And when we touch, so we will switch from the control of aerial propellers to the control of underwater propellers. For the underwater propellers, they are not the same as aerial propellers. So we will not have to take care about how we control these aerial propellers to work inside water, because we will switch the control of the others. But the idea is to keep one same controller for both. This is the idea. And the challenge, as I told you, it's beyond the problems that I mentioned here, the high value dynamics, the disturbances, and so on. How we can manage this transition going from the air inside water, and how we can do it with one controller. This is the big challenge.
I think power will do this.
Huh?
Power.
Sure. Yeah, sure. Exactly. You are right. Yes, power. Exactly. Autonomy. It's a big problem also. Yes, sure. But beyond that, for the first step, we will not consider this power problem. We can focus on the control itself, and this transition, when we touch the surface and go down inside water, how the controller should work. This is the big problem. Please.
Yeah, thank you so much for the presentation. Very inspiring.
Thank you.
I want to ask you about one of your slides, I think it's number 44, where you were talking about bio-IUV.
Uh-huh.
And then you've mentioned that you've used some of the AI technology. So tiny yellow for perception, and probably also you have used something else for the acoustic signals.
Here?
Yeah. So just a bit of background, I work on the safety of AI system and robotics, and I'm very interested to know what challenges those components have raised, maybe in terms of control or anything else when you were actually running the experiments.
Yeah.
Okay.
Yeah.
Did you notice anything?
Yeah, I understand. Yeah, very nice question. Actually, here, as I said, what we proposed here is a solution that combines two kinds of feedback. Okay. First of all, we start the feedback, which is using the acoustic signal. So, as I told you, the robot has 3 hydrophones here, and this is a finger. It's a device that emits acoustic signals. And when we measure this signal coming from here, the acoustic signal by these 3 hydrophones, we can detect the position of this finger, where it is. And then we control the robot to orient the orientation of the robot to go towards this finger. And then we control the surge to go there. What we notice using the finger is when we arrive here, we continue turning around because we cannot have a good precision. So this is the acoustic feedback. Then we try the camera. The good thing is the precision. We can track with the precision a target. However, the problem of the camera, if you are inside the water and the visibility is not so good, you cannot see the diver. This is the problem. If the diver is far away, you cannot see the diver. If the diver is behind the robot, you cannot see the diver. So these are the limitations of the camera. However, when we combine both, the good thing is we can see the diver at any place because of using the finger. And when we combine them, if we can see the diver in the field of view of the camera, we can rely on the camera and the finger at the same time. We do the data fusion, and the data fusion is done by the camera feature. If we cannot see the diver, we will switch to a control based on the finger alone, the acoustic signal alone. Now, the question, did we use AI here? Yes, we use AI here. And we use a deep learning algorithm, and it was for the detection of the diver. Because when we start the experiment, here, as you can see the diver, based on the camera, we try to detect the diver. So the algorithm, so what we did, we downloaded a lot of videos from the web, and we developed a training algorithm, and they remember the student make the algorithm training all the night during maybe 8 hours of training, and in the morning, the network is training. So we do the application directly, and the diver is moving. When we see the diver directly, the algorithm tells you, oh, this is the diver. So we switch the control based on the camera and the pinger acoustic signal at the same time. Now, in terms of security, in terms of challenges, so we have the problem of the computing time, we have the problem of implementation itself, and we have the problem of how we can detect, how we decide to switch between the pinger alone or the pinger and the camera at the same time. So this is the proposed control solution, but in terms of security here, we didn't do anything. We implemented, and also in terms of deep learning, we didn't develop a new algorithm. We used an existing algorithm, but we trained in this case, what we combine. But here the novelty is to combine these both signals and to run this experiment in a real condition. And this was near the harbor, and the visibility was not so good. In a few meters, you cannot see the diver. So the novelty was to do these two feedback and to switch automatically based on the data fusion.
Thank you.
You've got one question
Yeah.
online. Oh, sorry. Sorry, go ahead.
What is the protocol you follow to to tune the parameters? So you tune first the simulation, or you deploy the robot and then you try to tune until it works? Because we saw it.
You are right. Very nice question. All the not only for this, all my applications, we did experiments. All the controls have been implemented experimentally. First of all, it's very good question concerning the tuning. If you have a simulation, you can compute perfectly the parameters. You have the dynamic, you have the mod, you have no problem. However, in real-time experiments, it's not so easy. One. Two, sometimes we develop very, very nice controllers. However, the problem, nonlinear, balancing, predicting what you want, very complex. The problem is sometimes you have a lot of parameters to be tuned. So you have 10 parameters, how you can tune them? So this is the big problem. And the second thing, also, all what we did as experiments, sometimes we do experiments, sometimes we go directly on the experiment. Sometimes we do simulations, and sometimes we do experiment directly. What we noticed is, if you do simulations and tune parameters, 99% you take the same control you put on real robot, it does not work. So you have to retune again. So this is the big problem. And as I told you, the problem is the complexity. So we do not have a systematic way to resolve the tuning for any control problem. However, in most of the publications, you can see an algorithm to follow to tune the parameters. Just have a look to the publication, you will see. So, you have 6 parameters. We will not start tuning all the 6 parameters at the same time. We keep some of them fixed, and we start tuning maybe 2 or 3 parameters. Once they are tuned, we go to the others. So this is what we follow mainly. But most of the time, it's a trial and error. We increase, we decrease, we stay flat. But I told you, don't start with all the parameters at once, because it will be very, very difficult. And unfortunately, it's a task that takes time. It's time consuming. And most of the time, so for any controller, maybe you take 2 or 3 days to have this task done, tuning the parameters, to have the good thing. However, what we did also, most of the proposed solutions, we tune the parameters just in a nominal case. So we take the application, put robots in a real situation, and we tune the parameters. Once we tune, we don't touch the parameters. It's finished. Then, like for parallel robots, we add the payload. We don't consider this in the tuning at the beginning, but the controller is robust enough to estimate maybe this added mass. Like for the underwater vehicle, the same. So we tune the nominal case and we add some uncertainties. We keep same parameters to show that the controller is robust enough. So this is what.
Thanks.
The question online was answered already. It's to do with how long it takes for the transition from air to water. I've just got a quick one, actually, following up on that. Have you thought about using reinforcement learning algorithms to help the optimization of the parameters?
It can be a solution.
Yeah.
But the problem is we have to do this in real-time experiments.
Yeah.
And it depends if it's possible to implement a real-time learning algorithm to do this in real time. And also, I don't know, for some applications, it's okay, we can repeat something and the algorithm is learning, but in some situations, we have to pay attention. If you do the application itself, you go for, the tuning algorithm, it goes for high parameters. Maybe it's dangerous for the robots, for the security and so on. So this is why Up to now, we didn't try this, but it can be a very nice solution. Now it's the student who tune the parameters manually, and he take care about the security. We say, okay, we go with small parameters, and we increase progressively. I will check the performance, and so on and so on. But definitely, we can try some optimization or learning methods to this. But the question is it possible to do this automation?
Yeah.
Whatever the application is, whatever the robot is, this is the issue.
Any others?
Yeah, please.
One question
Yeah, please.
about the amphibious one. As I understand, you said we are at it's the beginning of.
Yeah, exactly. Yeah.
Because the dynamics of those two vehicles are really different. The environment
You're
is
right.
different. That's why I don't know if it would be possible to have the same control algorithm that can be applied for the same, different system with different environment.
You are right.
Yeah.
It's very challenging.
Yeah.
The solution is not easy. This is the research. So we are just working on what we did actually. Let me explain. What we did actually is we developed a very simple prototype. It's under development. The prototype itself. We developed a pivotal planner, takeoff and landing aircraft. So we use just two propellers, okay, for the aerial part, and two propellers for underwater. So we have four propellers like that. And we guide this motion, we have just vertical motion. We have not X and Y, we have just Z motion. And we put this inside water, and we are developing this prototype. So now the dynamics, okay, you are right, it's not the same. However, pay attention, it's not completely different. I mean, if you look at the dynamics of the aerial vehicle, so you have the gravity, you have Coriolis, you have the damping, you have the control input, for underwater, the same general form, but for sure, if you look to the density of the air, density of water, it's like multiplied by 1,000. You are right, it's completely different. So, and as I told you, we don't have the solution yet, but it's very challenging, I agree. But we are working on to keep the same controller to switch from here to here. But then we have to consider in the dynamics also that when we touch here, the surface, we have to detect it. We need a sensor that tells us, okay, we touched the surface. Pay attention here, we have to switch. So, but it's
How can you realize we reach the water autonomously? Autonomously,
Yeah.
How can you realize we reach the water and yeah?
It's going on. We are working on. We will see once we can, but it's a real question. When we touch here, how we can detect that the robot touches the surface. I think there are some solutions. You can have some sensors when you touch water, it gives you a signal. Say no, touch water. But pay attention, it's not so easy also. Because like, look, if we land in vertical way like that, okay, it's something. If we land like that. If the robot, the half is inside water, half is outside. And this is more challenging. Which dynamic one will use for the underwater, for air? So, but it's under development. It's something which should not so easy, but we are working on this.
Thank you.
Yeah, please.
You see that one fitting into the hazardous environment. So if you're perceiving this viscosity or something, and it's not that predictable, like it could be fitting into that hazardous environment with the same controller, rather than
Actually, what we have seen as control solutions, no one proposed this solution. All the controllers, they consider one controller here, one controller here. When they touch the surface, they switch completely. They consider the new dynamics, the new propellers, the new parameters, and they switch to the new controller. And for the air, they use one controller. So this, all the solutions is like that, the existing solution.
And they use the one controller in a very extreme environment. So like maybe you're in a grain bar, you're in a grain storage, and the viscosity is very strange.
Yes.
Your control, the same one controller could go, oh, I could adapt.
We will try.
So more like,
we try control with a wide range of the parameters, and we try to adapt this when we detect. So, and also we can consider like a model-based controller. So the model here, we have one model, and the parameters are not the same. When we touch here, we use the same control form, like we compensate for nonlinear dynamics. Here we have nonlinear dynamics, we switch to the new nonlinear dynamics. So when we touch the water, we use the compensation of the new dynamic model. And then parameters, they can be adaptive also, saying, okay, when I touch, I will switch to the new set of the parameters.
Yeah, I think it's Chris Tuner here. She told me at one point to consider air as a fluid. Certain Mach numbers, the same Reynolds numbers kind of come into the same. Mach numbers, very high speed, hypersonic.
Hypersonic, yeah.
Yeah, you get the same fluid dynamics as if you're in water. from the
Yeah.
from the vortex shedding, or the impact's now quite substantial.
Okay.
So it's kind of interesting that if you do consider air as a fluid rather than water as air, you can do some of the same work.
Yeah, I see. But it depends also on the price of this. If it is, I don't know. Because sometimes you have very good technical solutions, but if the price is huge of the sensor.
Right, so it's just conscious of the time. So I think if we could all just give, I've got plenty of questions. Ahmed's will be around this afternoon. So let's just give them another round of applause for.
Thanks a lot.
Maybe